Okay, so let's see if we can word this correctly. Please excuse any mistakes, but I'm sure you'll get the hang of it. Here we have two DC permanent magnet motors. One is our EMF and the other one is our counter EMF motor. So what this is going to do, it's going to show us how the current, or the self-induced current, which is produced by the counter EMF, reduces, and this causes a current flow increase into our motor as we apply a load to it. So we're going to be turning that back on for a start. Looking at the scope, our blue trace is showing us our current, our self-induced current from our counter electromotive force within the motor, and our yellow trace is going to show us the current being delivered to the motor. You'll see that when I adjust this pot and place a load on this motor, that our induced current flow through the motor will increase at exactly the same time that our self-induced current in the motor decreases. And this is of course because the motor slows down and the CEMF value decreases. So the same thing happens in coils, only ask about face. The current draw, as soon as you apply voltage across the coil or an inductor, the current flowing through it is at its minimum at that instant of connection, due to the CEMF value being at a maximum. With the motor, of course, being the other way around, as soon as you start it up, the current draw is at a maximum because the motor is at its slowest RPM, therefore the magnetic field change in time is the lowest value. As the motor speeds up, the magnetic field's change in time increases. That is of course the rotor windings or coils on the rotor passing the permanent magnets, and that increases our CMF value, which increases the current flowing against the induced current from our power supply into the motor. Okay, so once again our blue trace is going to show us our self-induced current value from the CEMF, and the yellow trace is going to show us our induced current from our voltage placed across that motor. The meter up here is going to show you the current value that the motor is drawing, and we can see what happens as we raise and lower the load on the motor, which in turn raises and lowers our counter EMF value and therefore the self-induced current. Right, so we will start it up. One of these motors has got a noisy bearing in it, so it's a little bit noisy, but hopefully we'll be able to speak over that. So at this point in time, this is probably simulating the motor free running without a load. You can see that our current flowing through our motor from our power supply is greater than our self-induced current produced by our CEMF, and we are seeing 18 milliamps over a 1 ohm resistor, and that is the current flowing into our motor. As we increase the load on our motor, we start to see the motor has slowed down. Our magnetic field's change in time has decreased as far as the rotor windings are concerned. So our self-induced current is now dropped, which in turn raises the induced current flowing through the motor, as we can see on that meter there. The more we load the motor up, the more you can see our counter EMF current or self-induced current drops because the motor is slowed down, and now our motor draws more current, as you can see on our meter over here. So we can now say the motor is under full load or a heavy load. We can see that our self-induced current from our counter electromotive force is near zero in value, but our induced current flowing through the motor from our power supply is now very high. We now have 1 amp of current flowing through that motor. As we reduce the load, once again you can see our self-induced current rising, which is against the current flow flowing into the motor, and so reduces the amount of current flowing through that motor. So right about there we may have a no load situation other than resistance from our brushes and bearings, and we can see that our self-induced current from our CEMF or back EMF as it is known is slightly less than the current flowing through the motor from our power supply at this moment here. Of 20 millivolts across 1 ohm, it'll be somewhere around 200 milliamps. And that's the way it works. If our EMF and CEMF or back EMF were the same value, as they are there, and I can't really adjust it absolutely spot on with this wire round pot. But we get the gist of it. Our motor, if it was ideal, is now drawing no current because our EMF and CMF values are exactly the same, or the current values produced by the two. So we know the motor's always going to draw current whether it's got a load on it or not. So that means that the EMF and CEMF can never be the same value in the motor. The CMF will always be lower than the EMF, and that's just what we have to live with because we do not deal in ideal components. What happens when our CEMF value or back EMF becomes greater than our EMF is this. So now the current, self-induced current from our counter electromotive force is greater than the EMF current, in that we actually don't have any current being drawn from the power supply. As you can see here, we now have negative. I'll turn that light back on so make it a bit clearer to see. We now have a negative value of around 750 milliamps, which is flowing out of our motor now. So an inductor would work very much the same way. When you first try and get that a little closer to 0. When the voltage is first placed across your inductor, the very instant that happens, your EMF and CEMF current values are identical, and then over time you would see magnetic field slowly decreasing and change over time, and your EMF induced current starts to become much larger than the self-induced current from the CEMF on the inductor, until such time that once again, like our fully loaded motor, which of course fully loaded would be stalled, but in this case, just for visual purposes, we can see we are no longer have a changing magnetic field in that inductor. We no longer have any self-induced current being produced from our CEMF, and we now have our steady state current flow through our coil. Which, if I turn the pot right up, in this case once again is just over 1 amp. There you go, that's how we can show the effects of loading a motor and what that has on our current draw and why it has it. Because as we load the motor slows down, which means that the value of our counter electromotive force decreases, and the value of the self-induced current flow from that CEMF also decreases, which allows a larger current flow through our motor. So a heavily loaded motor, no self-induced current to oppose the current flowing through the motor. Free running motor, the self-induced current acting against our induced current would be very close, and so the motor draws very little current, because the current produced from our CEMF is impeding on the current flow that wants to go through our motor. And if we had a really good motor, one we're all chasing, it would look something like that. Whereas now we have more current flow being produced from our counter electromotive force than what we have flowing into the motor, which is now not flowing into the motor, it is now flowing out of the motor, because our difference in current is now reversed. So it's as simple as that. And of course we turn it off and nothing flows. Alright, I hope that was able to explain some things to you, and I hope I got it all right. Although some of my wording may be a little erratic here and there, I'm sure you get the general idea of what was going on there. What you're seeing is exactly what happens inside a motor, and we can also show with this system exactly what happens inside a coil. So unless the current, self-induced current from the counter electromotive force or back EMF is higher than the current flowing through the motor, no current will ever flow back to the battery like we all want it to. In everyday situations, because we don't deal with ideal equipment, the current flowing into the motor will always have a greater value than the self-induced current from our counter electromotive force. Okay guys, thanks for watching, and no doubt we'll see you next video.